This one is already sent to you by the teaching assistant. This is new, and it'll be sent to you probably. By the way, we're using the second edition of the book, so you should get the proper numbers from the second edition. It's time. Are we on time now? Is it 40 past? Yes? Okay.
1 minute.
1 minute? Okay, I'll just wait for 1 minute. Okay, just copy down the problem sets and then you can start working on them. I'm going to continue a little bit with directions. And let's just talk about unbounded LPs first. Remember, the direction of a polyhedral set or a convex set is any non-zero vector D such that if you pick a point in the set and add a positive or non-negative multiple of that vector to the feasible point, you still continue to stay in the set. That's the definition of a direction. And if we consider a polyhedral set, so let P be a non-empty polyhedral set in Rn. And let's consider the following linear program, and consider the linear program minimize Cx subject to x in P. If P has a direction D such that the cost vector C times D is less than 0, then the optimal cost for this LP is minus infinity. The problem under consideration is unbounded. Under what circumstances? If there's a direction D whose dot product with C is less than 0. Of course, what this means is the angle between minus C and D is what? Less or equal to? Less than 90 degrees, right? That's what it means. The angle between C and D is greater than 90, so the angle between minus C and D is less than 90. That's what it means. And the movement, for a minimization, the movement in the feasible region in the direction of minus C makes you go down in objective function value. Or if you move along the direction C, you go up and up, further up. If you move along the negative of the cost vector, you get smaller and smaller. So whenever you have a direction D whose angle to the negative cost vector is less than 90 degrees, you can get smaller and smaller indefinitely with no bound. Why is that true? That's pretty obvious, actually. So let X be a point in the polyhedral set P. Then assume such a D exists. Okay. Of course, D by assumption is non-zero. Then a feasible point plus any non-negative multiple of D added to X is also feasible. So this is inside your feasible region. for every choice of lambda that's non-negative. Okay? Accordingly, what do we have? If you take the objective function value relative to any such point, what do we get? We get Cx, the value of the objective function at the point x, that's Cx, plus lambda times C times d. But C times d is less than 0 by assumption. Okay? Which means, of course, if you take your lambda to be a positive number, you're adding a negative number to the old objective value at the point x. So you get smaller. And of course, you can make your lambda as large as you wish and get smaller and smaller. So we can choose lambda as large as we want, and the conclusion follows, okay? And you get smaller and smaller. Of course, the reverse of this, the converse, is also true. Whenever the optimal cost is minus infinity, there must be a direction that satisfies this property. Of course, for maximization, CD must be positive rather than negative. Okay? I'm not going to argue for the second part. You can just do it on your own. It's straightforward. Okay, let's just continue with a little bit more. Now, this is a useful observation. The only thing with this, well, it's not a problem, but either you must know such a direction in the first place to be able to conclude that the LP is unbounded, or if you don't know, then you would have to try different direction vectors D. But there are infinitely many of them, uncountably many. So you want to be able to, if you have to do this, you want to be able to do this using a finite set of directions rather than infinitely many directions. Okay? It turns out that there's a subset of the directions of any polyhedral set which actually accomplishes the what we're trying to accomplish here. And what subset is that? That's the set of extreme directions, which I haven't defined yet, but that's what we're going to do now. So let's talk about extreme directions. First, let's define two directions to be distinct. Two directions of a polyhedral set are distinct if one is not a multiple of the other one. Positive. One is not a positive multiple of the other. So, for example, the directions 1, 2 and 2, 4 are not distinct because they all point in the same direction. Okay? One is a positive multiple. It's twice. The second one is twice as much as the first one. Whereas 1, 2, and 2, 5 are distinct. Okay. That's the definition of that. A direction D of a polyhedral set or a convex set S in Rn is an extreme direction if D cannot be expressed as a positive combination of two distinct directions of the same set. If D cannot be expressed as a positive linear combination of any two distinct directions of S. So, you should not be able to find two distinct directions, which gives you D if you multiply one of them, say D prime with alpha, the other one with beta, where alpha and beta are, should it be non-negative or positive? Let me just check that. Yeah, positive. Where alpha and beta are real. If you are able to discover alpha and beta relative to some two distinct directions, D prime and D double prime, then D is not an extreme direction. If you're not able to do this, then it is an extreme direction. Okay? All right. Let me give you, let's look at the previous example we worked on. What was that example? X1 minus 2x2 greater than or equal to 6, or minus 6 actually. And x1 minus x2 greater than or equal to minus 2, x1 and x2 non-negative. Well, in the previous lecture, we actually plotted this, the feasible set, polyhedral set. So this defines a polyhedral set P. And then we looked at the directions. So the directions must satisfy the same set of constraints, except that they should be homogenized. Okay? The right-hand sides must be all made 0. So to find the directions, you need to inspect. Let me change this to D1, D2 greater than or equal to 0, D1 minus D2 greater than or equal to 0, D1 and D2 both non-negative. Of course, number 3 and number 4, they don't change. They are already stated here. The other ones, the right-hand sides, are changed. So all of these constraints are now passing through the origin. Okay? You moved the original system. I don't know what they look like. I remember they looked something like this. All you do is you retain these two, number 3 and number 4. And then you moved number 1 and number 2 to the origin parallel to themselves. So this is one of them, and the other one is like that. And when you look at the shaded region, which is the intersection of all those half spaces defined by the new set of constraints, this is what you've got. So this contains the set of all directions for this polyhedral set. And there are two extreme directions here. One of them is pointing this way. The other one is pointing that way. Okay? There are exactly two for this particular example. How do you find them? Well, one way of doing it is to do the following. Let's just number these as 1, 2 prime, 3 prime, 4 prime. Okay? One way of doing this is, since I know that 3 and 4 actually impose non-negativity, I can just add a new constraint which normalizes the components. Okay, so the absolute value of the first component plus the absolute value of the second component add up to 1. When you normalize this, you're forcing the d vector, d1, d2, to be non-zero. At least one of the components will be non-zero. Number two, since d1 and d2 are already required to be non-negative, of course you can write the absolute values in linear fashion like this. Okay? So this is new. I'm just adding it. So add. That's the normalization constraint. Okay? And the effect of that is it just slices through the feasible region like that. That's the new constraint. And so you have to be on that line. It's an equality. So now the feasible set degenerates, or well, it degenerates into this line segment, the red line segment, the cross-hatched portion of that segment in the feasible, the old feasible region. So this is the solution set for 1 prime through 5 prime. Whereas the black shaded region is the solution set for 1 prime through 4 prime. Okay? When you do this, of course, you are identifying two extreme points for this particular set. Okay? And it's easy to find them. What do you need? To find extreme points of the new set, you just need to look at them two at a time as equalities. Well, one of the equalities is supplied by d1 plus d2. That should always be inside, okay, or should be always enforced. Then you can choose one of the other inequalities as being active and see what happens. For example, if I choose 1 prime, do I get a solution? Let's just try and see. d1 plus minus 2d2 equals 0. If I get this, so I'm imposing 5 prime and what is that? Number 1 prime. Okay? This may or may not give a basic solution, an extreme point. So does it give or not? So if you multiply the second one by minus 1 and add it to this, you get 3d plus, 3d2 equals 1, which gives you d2 being equal to 1/3, which of course tells you that d1 must be 2/3 because of the normalization. Okay? So this is the vector 1/3, 2/3, and it's, which one is that? It's this one, okay, in normalized fashion. So that's the point, 1/3 and 2/3. If your intercepts here are 1, 0, well, actually 0, 1, and 1, 0, okay, for the red line. Okay. Of course, any positive multiple of this is also a feasible direction. So 1 and 2 will also work. Okay? It's an extreme direction. It doesn't matter if you multiply them by a positive number. But with the normalization, this is what you get. So up to a positive constant multiplier, you specified all that needs to be specified. What is the second one? You again impose 5 prime with something else. Which one is that? In that case, d1 is positive, so we're imposing 3 prime, I believe. In that case, of course, we get d1 plus d2 equals 1, and d1 equals 0, okay? Which gives you, obviously, the direction with d1 being 0, the other one being 1. So that's 0, 1. Or 1, 0, sorry. 1, 0. Second direction. No. 0, 1 or 1, 0? Well, that's not a direction, though.
We had better take the fourth constraint.
The fourth one? I want the fourth one, not the third one. Huh? But this is not a direction. Because, well, it's not a direction. It points this way. And it should be violating at least one of the constraints. Which one does it violate? 0 minus d2. Number 2 prime is violated, okay? So this is violates 2 prime, which means not an extreme point of the enlarged set with the fifth in, 5 prime in, not an extreme point of the system defined by 1 prime through 5 prime. But if you replace 3 with number 4, then you get what you want. And this one gives you 1, 0, and that satisfies all of the constraints it should. I'm not going to check it. So this is an extreme point, extreme direction. Okay? All right, I guess we have it all ingrained in our minds. Huh? Is that clear? Okay. So that brings us to the discussion of how to represent polyhedral sets in terms of their extreme points and extreme directions. That's a useful representation. So let's talk about that. I don't recall if I defined a convex hull for you or not. Did I do that? Does anybody remember? What's a convex hull? Well, if you have finitely many points under consideration, the convex hull of a finitely many set of points is the set of all convex combinations of these points. But the more general definition is, what is the more general definition if you don't have a finite set under consideration? If you have infinitely many points, for example, or if you have...
The convex set for which the all extreme points are...
The convex combination is equal to the polyhedral set?
No. You can also, the convex hull... Well, let's not go into the infinite set. Yeah, you can always define it to be the intersection of all convex sets that contain these points. In that case, of course, you have infinitely many convex sets that intersect these things, but let's not go into that. Let's just go with the simple case. The convex hull of a bunch of points, say x1 through xk, in Rn. All of these are n-dimensional vectors. The convex hull of x1 through xk in Rn is the set of all convex combinations of these points. So we're talking about the set of points of the form lambda I xi, where lambda I is a number between 0 and 1 for every I, and lambda I add up to 1. And so lambda I xi summed over I gives you the set of all such possible points. Okay. So, as an example, in 2 dimensions, suppose you've got these points, x1, x2, x3, x4, x5, x6, x7. When you start taking all convex combinations of these points, what you will generate is this set here. Okay? That's the convex hull of these 7 points in the example. So the representation theorem says the following. I don't know what number we are at. I omitted a bunch of proofs, so I forgot now where we are. Are we at the 8th one? That's what I remember. 8th? Okay. Theorem 8. Let P be a non-empty polyhedral set or non-empty polyhedron in Rn. And let's assume P does not contain a line, meaning that it has at least one extreme point. Assume P has an extreme point. Let x1 through, say, xk be the extreme points of P for some positive integer k. And let, say, d1 through dl be the extreme directions. Extreme directions of P if they exist. An extreme point exists by assumption. The extreme directions may or may not exist. If they exist, you number them from 1 through L. Let Q be defined by the following. You take lambda I xi, I going from 1 to k, plus you take, say, mu j dj, j going from 1 to L, and you form a point when you add them up. Here, lambda I are constant, well, not constant, but lambda I are real numbers between 0 and 1 for I going from 1 to k. Mu j are real numbers. Well, non-negative numbers, yeah. Mu j are non-negative numbers for every j going from 1 to L. And last condition is the lambdas add up to 1. They are normalized, non-negative numbers. That's the end of your definition of Q. Now, in this definition, of course, let me have your attention for a moment. In this definition, what you're doing is you're taking a convex combination of the extreme points by choosing your lambdas. Plus, to it, you are adding a non-negative combination of the extreme directions if the extreme directions exist. Okay? Of course, mu j's can be 0. That you can pick all of those to be 0, or you can pick some of them to be positive, whatever. But nevertheless, you generate many such points of this form. And Q is the set of all such points that can be generated in this particular fashion. And the claim of the theorem is the polyhedral set is the same as Q. Okay? Whatever the polyhedral set. The polyhedral set is initially defined by a bunch of linear inequalities and possibly equalities. Okay? It has nothing to do with these extreme direct. Well, it has something to do, but you know the definition of P is in terms of half spaces and hyperplanes. But then this definition Q is in terms of extreme points and extreme directions. So we're in a different domain now. Okay? All right, so this is the claim. The proof, I'm going to omit the proof, but the part that says that, which part is trivial in your judgment? Q subset of P. Yes. Q subset of P is trivial. Why is that trivial? Because if you take any non-negative combination of the extreme points and non-negative combination of convex combination of extreme points and non-negative combination of extreme directions, because your xi's and dj's are actually, xi's are points in your feasible set, dj's, when you add multiples of dj's, positive multiples to feasible points, you still continue to stay in the feasible set. So any point picked from Q will continue to be in P. That's trivial. 3 lines, maybe. Okay? Proof. I typically write it in 1 line, but sometimes, of course, you give additional explanations. Okay, 5 lines at most. Okay? The other part, proving, so this is straightforward. Then you have to, of course, prove that P is a subset of Q. This is not straightforward at all, because you need to go into subspace arguments and you need to do induction on the dimension of the subspace, so on and so forth. So I'm not going to prove it. It's involved. It would take approximately 20 minutes to go through that proof argument, or maybe 30 minutes. Instead of doing that, I'll just illustrate what this amounts to by means of some example situations, and then you get the main idea. Okay? Once you get the main idea, then you can work out the proof. All right, so let's look at an example. Well, this is not an example proof, but you can think of it as an example proof for the bounded case first. In the bounded case, of course, there are no extreme directions, so we just drop that part out. In that case, you have a bunch of extreme points of a feasible set under consideration. So I've got x1, x2, x3, x4, x5. So we're talking about essentially the second part, except that as an example situation. So I pick a point, I don't know, let's pick some x here. You pick a point x in P. And you should show that that point also belongs to Q. That's what you want to show. So you pick this point, and then since the set has at least one extreme point, you pick an extreme point. For example, I pick x2 as my extreme point. Okay? You are able to choose such an extreme point. Once you do that, you can form this vector, which is your x minus x2 vector. Oops. Right? Okay. So I picked x and p, and then I picked x2 and formed the vector x minus x2. This is my direction vector. It's non-zero, because if it's 0, then x is one of the extreme points, x2 in this case, in which case, of course, it will be in Q. Okay? So you assume that it is not the case. And so this is a non-zero vector, of course. And then what you do is you add to x a positive multiple of this direction vector. And when you do that, of course, you move along the same direction. You know, you continue to move. Depending on what your lambda is, you are either here or here or here or here, wherever you are. Okay? But if you take a particular point here, this will be x plus lambda d, where d is defined in this way by definition. Okay? So maybe we should also put rd here. Okay? So you choose a particular value lambda bar for lambda, which takes you all the way to this point. So that point is a particular type of point. It's x plus lambda bar d. There is such a lambda bar, okay, a positive lambda bar. Why is there such a lambda bar? It's bounded, yes. Because at this point, this particular constraint, whatever that constraint is not active. Then when you start increasing your lambda from 0 upwards, eventually you hit this particular constraint, you make it active. At that point, of course, at that point, this particular constraint will be active, but if you go further than that, of course, it will be violated. Okay, so there's a particular such lambda bar. And once you choose your point, x plus lambda bar d, then there's an inductive hypothesis in this. This is a lower dimensional space. We're in two-dimensional space. But now we are on one of the constraint lines, one of the hyperplanes, active constraints. So the dimension goes down by 1. So if your induction hypothesis says that for dimensions up to the dimension of the space under consideration, but less than that, if the property holds for that, in other words, if this whole statement holds for that, then you are able to show that it holds for the space under consideration. Okay? So, by induction hypothesis, we know that this is expressible as a convex combination of extreme points. In this case, of course, x is some, say, alpha times x4 plus 1 minus alpha times x5. We know this by induction hypothesis, okay, on the dimension of the space. That's why this is involved. You know, I'm cutting through many of the stuff, but that's the main gist of the whole thing, okay? And so from here, this is in the lower dimensional space. From here, we should be able to show that x is, in fact, a convex combination of the rest. Okay? I know that, well, that's not x, by the way. That's x plus lambda bar d. That's what I know. Okay? We also know that x is equal to, or x, well, let's see. What is x equal to? Well, x is the picked point. So let me give a new name to this point. Let's call this x bar. So this is your x bar. And x bar is equal to the old point x plus lambda times x minus another extreme point x2 with lambda bar. So how do we express x as a convex combination of the points of interest here?
Convex combination of x2 and x bar.
Okay, x is, from the picture you can see that, it's a convex combination of x2 and x bar. So there's a beta, which you can figure out, which multiplies x2, and 1 minus beta, which multiplies x bar, which gives you x. Okay? And of course, continuing from the boxed expression here, this gives you 1 minus beta times x bar, which, what is x bar here?
I513 plus 1
Okay, just a second. I better use this information here. From here, x is equal to, well, x bar is equal to alpha x4 plus 1 minus alpha x5, right? So everything here is an extreme point. So the multipliers in front of those extreme points better satisfy the 0, 1 interval requirement, plus they should add up to 1. Do we have that? Beta x2 plus alpha times 1 minus beta x4 plus 1 minus alpha, 1 minus beta x5 plus, of course, 0 times x1 plus 0 times x, what is that? 3. Okay? The missing ones. Now, beta is a number between 0 and 1. So, beta is between 0 and 1. I know that for sure. Alpha times 1, well, alpha is also between 0 and 1, so alpha times 1 minus beta should be between 0 and 1. And this one, again, should be between 0 and 1, because you're multiplying two numbers between 0 and 1. And do they add up to 1? I don't know. Add them up and see what happens. Beta plus alpha, they do. Who said that? Who said that they do? You do? Okay, I believe Sibel. They add up to 1. Okay? Did you figure it out? Yes, okay. I don't know. Beta plus alpha minus alpha beta plus 1 minus beta minus alpha plus alpha beta. So minus alpha beta plus alpha beta. And then beta and minus beta goes. This and that one goes. Yeah, you have 1. Yes. Thank God. Otherwise, I would be in trouble. That was for the bounded case. For the unbounded case, you have a more complicated situation. So you've got some kind of a unbounded polyhedral set, such as this one. Okay? There are two extreme directions here. One is this, the other one is this. So what you do is you pick a point X in the polyhedral set, and then you move this point to a point here, say X bar, by taking a non-negative multiple of X and adding to it one of the extreme, or maybe both of the extreme directions. So let me see. Yeah. So you're expressing X bar as a old point plus, say, some mu1 times the first direction. In this case, we've got two directions. Of course, these directions are situated at the origin, okay? So remember that, okay? So the origin is somewhere here. There's D1 here. There's D2 that points this way. So you're taking two multipliers, mu1 and mu2. In this case, let me just choose, because my line looks parallel to D2, let's just choose mu1 to be 0. You don't have to, but let's just do it that way. And so mu2 times D2 will be that. And you will get your X bar. Well, this should be reversed though, because I can't really go back here. What I should be doing is I should be writing X as some X bar inside the convex hull plus the direction. Okay? So X is equal to X bar plus mu1 D1 plus mu2 D2. That's what I should do. I can't go back, okay, with a positive number. All right. So once you pick X bar here, there are extreme points x1, x2, x3. So X bar is equal to, say, alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. Okay? Then, of course, X equals X bar, which is alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus, that's X bar, plus mu1 d1 plus mu2 d2. I'm using this here, okay, and that. And we have what we want, because alpha I are between 0 and 1. For I going from 1 to 3, they add up to 1. How do I know that? Because X bar is a convex combination of these extreme points. It's picked from the convex hull of the extreme points. Okay? So that gives you a convex combination of the extreme points plus a non-negative combination of the extreme directions. Okay? Which is what we wanted to have. Let's stop here for 10 minutes for the take a break, and then we continue.